In this video we'll set up the LM900 to read the analog input and control the analog output. The difference here from TwinCat, we're using TO Portal and we have a different library. It's the same but it's adapted to this platform. We won't be having any additional tasks, we'll be having one task. On a Siemens PLC you can run several programs. We'll have our main OB1, that's our main program. We could have several. They will be then executed by the lowest number first and then the higher numbers of OBs. You have several to choose from, but if you want more programs you can add another one. And then the number would state which program to be run first, second and so on. You can also have other kind of OBs or programs. Some of them useful, like this one, if you screw it all up. But there's no kind of tasks that we had in TwinCat, so there will be some differences, among other differences. So let's get started. Our main program runs from top to bottom. You can change the programming language. First of all, we'll read an input. And we'll use the MA template for that. We already have the IO list configured. All of that is covered by a different video. So this is our MA. Connect the input tag. And to get the cycle time, we could use the built-in type of blocks. We could get, let's just have a look at it. We could enable the system and clock memory and use those tags that are generated from that. That will make this a Siemens specific program, so we're not going to do that. We'll just use exactly the same as we did with TwinCat, add our own block, and call that common. And exactly like we did on TwinCat, there you go. So that's our MA and common block. And then we had the output that was to be controlled. Control of analog. Let's call that pump 1. The output, pump 1. The input is the calibrated, filtered, all nice and clean lever transmitter output. And let's smack on this. Lock safeguarding low if we have an alarm high. Just in here, configure. Configure, all configured. So that should take care of most of that. Now in TwinCat we had a configuration view on top for the whole program. We still have that. But what's kind of different here is that we have something called global DBs. So this is the DBs, so the data blocks. As you can see here, from this function block, its single instance memory is the DB called LT9001, and similar for the CA. So instead of finding it on top here, when we're using it in the OB1, we'll have it here. So to find the parameters for LT9001, we'll go into here and find that. Now, on the standard modules for backoff, the analog values are between 0 and 32,767. And that's not true for most Siemens modules. All the Siemens modules that we have, they are more of something like 24,000. And then you use the remaining up to 32,000 to define some out of range values or whatnot. Anyway, we're using 0 to around 12,000 since we're reading 0 to 5 volts, and our input cards and output cards are plus minus 10 volts. So we'll be using half and then calibrate the rest. Somewhere around this number is correct for 5 volts. Add some filtering, tag name for display, maybe use a couple of them for averaging. Set some limits in engineering units, something like that. Maybe a delay, some hysteresis. Output value will be 0 to 100%. And we will disregard anything lower than 2%. So that's configured. Now for the pump. Tag name for display. dB, let's say if it's in between 2% of the final value, it should start considering not changing the input. Out channel, this too is not 32,000, let's say it's somewhere around 12 again. And you'll have to tune that. Zero to 100. Let's initiate these to something we know will fit okay. It is not reverse acting, it's direct acting. Let's put some limits on the rate of change of set point, limits on the rate of change of output. Yeah, that should do it. So that's the CA and MA configured. Good to go. Just connect it up and around. In the next video we'll set up a simulator. In this video we'll set up a simulator for the LM900 using the TIA portal. In the last video we set up a simple measurement of an analog signal, the lever transmitter, and control of an analog output, the pump. So let's set up a simulator. What we will be needing now, first off, is to run the simulation at the start and end of each scan of the main OB1, the main program. The output tags doesn't necessarily have any memory, so we'll make our own. Let's make a new data block, a global DB called sim, and then make a struct for the I/O. Sorry. There we go. Two integers and some Boolean values. Going back to main. The last thing we're going to do when we're simulating is copy. isn't that necessary. Let's just use this one and copy the tag. So the output tag is now copied to the data block dbsim and stored. So let's find some kind of simulation for it. Tank, sounds good. And let's say this will be controlled by the pump. The pump output is, what was it? 0 to 12,000 or something like that. So it's 0 to 12,000 going in here, that doesn't really match. We need 0 to 100%. Let's see here. Some ASCII art. Yeah, percent. So we need to convert that. And there's a nice hack for that. Keeping it all in one network. Every network needs a terminator or a sink. I like this trick here, just for the view of it. So let's add an analog input where we take this guy and then the raw integer value for that should be in the CA. There we go. And the minimum value as well. So now we're converting it from 0 to 100%, and then we need to dump the scale value somewhere. There we go. This OR gate here doesn't do anything, it just allows me to cram all of this into a network. So first we convert this analog value 0 to 12,000 to 0 to 100%, dump it in here. And you can play around with this thing if you like. Maybe we should have some kind of volume when we start or not. We can play around with the cycle time. We'll use the same as the rest of the program, but we could mess with this to speed up the simulation. Don't speed it up too fast though. Some parameters you could set or not. So if we have this command from the pump, something goes into the tank, the level increases or decreases, and we need to convert that again to our level transmitter or simulated level transmitter. It's not really that necessary to use a temp variable here. Why not? Dump it into here. There we go. 0 to 100%, 0 to 100%, and out 0 to see here, maximum input. Did we get that one right? Yeah, maximum in, minimum in. It's not too happy with receiving a real value here into an integer value, but it should be just fine. And this is our simulated level transmitter. So when we start this program, we do the command block, and then we do the simulation with the stored value of the pump output. Simulate the tank, and then use the simulated level to simulate the level transmitter. Then we can use it. And on the last scan we copied the output from the program to our data block to store it. So that's how to set up the simulator. In this video we'll pretty up this program from the earlier videos, and we'll add a button to enable simulation, and we'll add an HMI. So first of all, let's take a look at this. It's all kind of messy. We have a network for the common block, first scan of the simulation, an input, and we have an output, and nothing in between. And then we have storage of output values for the simulation. What we'll do now, first, add something in between. This will be this condition evaluation. So we can combine some inputs to some smart logics. Then, well, all of this is all nice and short now, or at least short, maybe not nice. We'll divide it into functions, just to pretty up. So the inputs copy that over here, delete this one, and replace it with a call to the FC. If you go into here, you'll find exactly the same. So we're just tidying up. Then we'll need the same thing for condition evaluation. We'll add something nice into there later. Outputs. Still just one output, but let's make this kind of scalable. And then the simulations. Oops. Yeah, that's all good. Now then, still have our common block in the main OB1 program. Then we do the simulation first scan with calculating everything, the stored value of the outputs from the last scan. Then we'll read our inputs. do some condition evaluation, and output something, and then you have the simulation. So the button that we're going to make, oh sorry, we already have the DB here. We'll add a boolean for that, enable sim, and then we'll only run these sim blocks if we have enabled simulation. Inputs still the same. We can add other inputs here. Condition evaluation outputs, all good stuff. So just to show some use of this, let's do a condition evaluation. Since we're controlling a water level in a tank, we have a level transmitter that gives us the water level, and we have a pump to control, an analog pump to control water flowing into the tank to fill the tank. We can improve our control by knowing how much flows out of it. And if you're into physics, that won't be too hard for you to figure out, but it is a constant times the square root of the water level, more or less. And you can check out Bernoulli and or even just the simulator for that case on how that works. So we already know it pretty well. Let's see here, flow into tank, flow out of tank, square root, some gravitational acceleration, all the good stuff, and the area of the valve and a loss coefficient. We'll dumb that down to something useful and call this network outflow now. The outflow now will be square root of something, specifically our height. Always nice to put the bits first. The reason for that is you often reserve 8 bits when you first make the first bit. So if you have a bit real, you'll waste lots of storage space. All of these addresses commonly start off at a even number. So if this is index 00 or bit number 00, this would be 20226. So instead of having 00, 20 to 60, and then another bit, which would be what, 60, to then 8.0, that's a waste. So instead you can just add all your bits in line first and then all your integers and reals. Anywho, then a multiplier. This guy multiplied by some kind of coefficient describing everything. The loss, the area of the pipe, everything. Let's make that something we can adjust. Global DB setup. And just call that outflow coefficient. And we'll set it to 5. So it's all in here now. Let's add another block. for every condition evaluation. And call this, let's structure this, outflow now. And while we're at it, outflow at target. We'll get back to that one. So this was our outflow now. If we have this level height, square root of that multiplied with this outflow coefficient, which describes the opening of the valve, the loss in the pipes, everything. Square root of this multiplied by this is our outflow now. So this one needs to be calibrated. Now this is the instant right now, and the next one, outflow at target, will be the same calculation, but instead of the actual measurement, we'll use the set point and then calculate that, work the target, and then calculate what will the outflow be when the water level is at target. The reference for the pump, square root of that times the same coefficients, outflow at target. So that's two condition evaluations. Now let's use it. This CA is basically just a PID with different modes. So the feed forward we could use with this PID would be to feed forward the water level. We could then use the outflow now, which will be susceptible to noise since it's based on a measurement, or we could just use the reference. Since we know that if we're going to be at the 50% water level, we'll need some kind of amount of flow, since that's what's going out of it. So luckily we already calculated this. So now we can choose to feed forward the outflow at target or the outflow now. So that's some use of that condition evaluation. So now we set up the structure for everything, at least this far, simulation. Now let's do the HMI. We have two types. You have a comfort panel at the lab. For this one we'll be using WinCC RT Advanced, a runtime that runs on your computer. You can also set this up like we did in TwinCAT with a web visualization. This is more like a team viewer that you can set up the smart server, or what was it? But let's not spend so much time on that. So this is the PC station running WinCC runtime, and we have a general industrial Ethernet card. We'll set up the IP for this as something on the same subnet as what we're connecting it to. Hold on. Here you'll see there's some stuff missing here since I haven't configured the entire LM900 project, but this should be in this subnet. So let's say we use this PLC 101. Now then, connections, HMI connections, this guy to this guy. If we go back to network, now we have the interface here. That's good. And then we have a HMI connection between these two guys. HMI connection 1. See here, looks good. Then some screens. It's called the first screen main. Let's do some settings. Maybe this size, not full screen. Here you can start the smart server and other good stuff. You can also do some clever things. We're not going to go into that now, just plain and simple. Back to the library. We have some face plates. We have a MA. Which has an interface laid out for it. And as we did with TwinCat, all we do is connect up the DUTs. The nice thing here, everything is totally integrated in the TIA portal. So you have your HMI system and your PLC system, as you do in TwinCat. So let's dig deep into the PLC and find the level transmitter and the operator station commands. That's mapped. And the statuses. Parameters, and this little treat, what do you want to trend? You would like to trend this guy. You can also add more to it, like limits, but that's the only difference from the approach that we used in TwinCat. Still exactly the same. This is allowed if the UDTs or DUTs, whatever you want to call them, are in the same library as your faceplates. If you want to make your own, just make sure that the DUTs are in the library. So that's the MA, and then we had a CA. So we reduced all our programming down to configuration. We could expect that with a decent framework and a decent library, 80% of all our PLC coding would be just parameterizing, setting stuff up, and leaving just 20% of custom code, project specific code, which would make us way faster. Just better at doing process control. There's no use in inventing the wheel here. So here we go. That's the CA setup. Let's add a button for the enable SIM tag. And if you press it, we want to invert a bit. Which bit? Well, let's dig deep into the PLC again. This guy. Looks about right. Maybe we should dynamize colors. Give it a nice blue, if it's on. And let's also add an alarm view. Yeah, that should do it. So let's try it out. Start the simulation. Simulate this. Let's see what it says here. Labels in. Sure. Let's give it some input. So this is 100%, nothing's happening here. So what's wrong? Let's Let's check out the inputs. Control T. It's going slowly up. There we go. It's a pretty big tank. So we could speed up the simulation, or we could just change the tank. To do that, let's see here. We could change the radius of the out, the height of the tank, the radius of the tank. So this is a 1 meter radius, 1 meter height tank. That's pretty big. So it's going to take a while to fill up with a garden hose. That was a 1-inch hose that was connected to it. By the looks of the numbers. So let's just leave it like that. Everything seems to be working. If we turn off the manual input, does the level decrease? It does. And if we give it a set point, 50% maybe, if I may, put it in auto. Yeah, that's gonna take forever. 20. And let's use our feed forward, multiplied by 1. We're not using enabled, we have not enabled external PIDs, so we're using internal PIDs 4 and 10. Sure. It's pumping as hard as it can. Yeah, that seems to work. Now then, if we're done simulating and you want to run this with a real PLC, there's one step that you need to do. You need to go into control panel, all control panel items, see if you can find the set PG-PC interface. And here you'll need to find how this guy is going to communicate. Well, that's not the one. Well, we're simulating now, so that's going to make this look a bit weird. But you need to get into this PG-PC interface, Google the problem if you have the problem. I already solved it at the lab PCs, but if you're using your own. And then it would be setting it to something like this, which looks like I already did. If it says none, you're in some, probably having some issues with running the WinCC runtime on with a PLC as a target. Just set the S7 online interface parameter assignment used to TCP IP. And that should do it for you. With all of that done, feel free to play around with all of this, especially these services, which can be pretty fun if you're into that. So that's how to set up the simulation and HMI for the LM900 using TIA Portal. In this video we'll add the Autotuner to our LM900 project, like the LM900 project continuing from the previous videos. We already have a HMI for it, looks like this. We already have some basic functionality done. Now we have an Autotuner that wants to do stuff to the CA templates in here, if you select it to. So we'll add a new network. We'll call it this main. This is where the magic happens. And we'll keep to our structuring. FC main. Before FC main, we've generated our common values. We've done a simulation first scan. We've read our inputs, simulated or real inputs. We've done some condition evaluation based on those inputs and previous outputs, by that matter. And now we're into the magic stuff. Not that magic though. We're just using a Autotuner from our library. So it's an FB Autotuner. There we go. That's an Autotuner for pump 1. So let's map what it needs. EA. It needs to know if pump 1 is currently in the Boolean state of automatic, if it's in the Boolean state of tracking. It also needs the error. Maybe I should have just added that as a parameter. Or, no, sorry, added 2 inputs instead and calculated within. But I didn't. So let's see if we can connect this. And add this. Just some temp variables. There are better ways to do this, but I like to do it this way. So let's calculate the error as the difference between the reference and the measurement. Tidy up. This guy here. Then we have our common variables. Start up. Restart. Maybe we wanna shut this down if we have a high alarm. Yeah. These are going to be used for the P1CA and the current gains also. Pump 1 auto tuner. So we configure all the inputs. Let's go to where these outputs are used as inputs instead of mapping them here, just to make it more structured. Which is here. So the Autotuner gives out a maximum and minimum manual input or a tracking input. So we'll put the CA in tracking automatically. The Autotuner does that. And then put it in tracking. This will be the tracking value. This will force tracking. That's one way to do that. And we can put it back into auto when we're done, or manual. These are options, but we need to give the Autotuner access to the commands. So the lock manual, lock auto, force tracking. Oh, sorry. Lock manual, lock auto, force tracking, and the actual tracking value. So that's all connected up, ready to test. So Control L, or this is the short key for loading, and Control T for monitoring. Reset the call environment. We did some big changes here. So let's see. Oh, never mind. All good now. So let's fire up or let's do the HMI a bit further and add a faceplate for the Autotuner. Alt-Enter is the short key for entering the properties. Now let's dig deep for the Autotuner parameters. Statuses. Enable theme is still running. We have some water in the tank. Let's set the set point to 15. And see if we can run the Autotuner. Well, let's not run the Autotuner. Let's do two things. We'll decrease the volume of the tank so this moves around a little faster, a little closer to the true LM900 model, which is not 1 by 1 meter or 1 meter radius by 1 meter height. And let's fix the tag name. Let's do the parameters for the Autotuner. And one more thing, I see we forgot to do. So let's do the simulator first. Let's make this guy, how high is it? Maybe 30 centimeters. Oh, that's the radius. Maybe 10 centimeters. That's a radius, and 0.3 as height. And let's load that. And if we go online here, we'll see that the values differ, since this is the start value and this is the actual value. So one thing we could do is just start and stop, or we can manipulate it. For this time, let's just start and stop it. Since we don't want to mess anything up. So how did that work? Enable the simulation. Yeah, that's much faster, so we don't have to wait forever. Now let's fix the tag name, and one more thing. Let's find the Autotuner parameters. 1.1 Autotuner. It's not reverse active. Let's add a threshold for where it switches between maximum and minimum input. Threshold for error. Stop options, let's put that to 2, so when it's done it leaves the CA in auto. Default gains, let's give it something that might work instead of something or nothing. This might work. Now let's see what's online. These differ. We could do it like this instead of starting and stopping. There you go. This one as well. Then they are equal. And then the last part that we forgot, or I forgot. We need to actually use the gains that are coming out of the Autotuner. They're also going to be used here. Whoops. Ah, come on. then move into pump 1 parameters external P IND Autotuner values. There we go. So now we actually use the gains from the Autotuner. We can do this right now. We're using these gains. And if we now do a step, it's pretty smooth and slow. So putting this to 10 wasn't really necessary. It was just a fuck up where I didn't notice that we wasn't actually using the gains. This is very overdamped. Let's try again. Up and down. 3 and 9. Cool. Let it down. And up again. Oh, there's no overshoot. Let's enable this guy again. Cool. So that's how to set up the Autotuner for TIA Portal and a bit more.